Hello, so far we have seen two scenarios in which an EMF can be induced. The first scenario is when you have a stationary coil sitting in a changing magnetic field. For this example here, this coil is experiencing an increasing flux into the screen, and the outcome is an anti-clockwise EMF in this coil. The magnitude of the induced EMF can be calculated using Faraday's law. The second scenario is when you have a wire or a conductor sweeping across a constant magnetic field. For the example shown here, the induced EMF will be such that this becomes the positive terminal. And the magnitude of the induced EMF depends on the rate of flux cut, which you can calculate using the formula BLV. So today I want to talk about a third scenario. A third scenario is when you have a coil moving in a constant magnetic field. For example, this rectangular wire frame moving across like this. Or it could even be rotating. Or it could be just a coil whose area is changing for one reason or another. So for situations like this, should we analyze it as a coil experiencing a changing magnetic flux? Or should we analyze it as wire segments cutting the magnetic flux? Well, let's try both and see whether they work. Let's use this as an example. We have a rectangular wire frame, 30 cm by 20 cm. Is moving at a constant speed of 5 cm per second across a uniform and constant magnetic field of 0.8 Tesla. We're particularly interested in these three stages of motion of the frame. The first is when the frame is entering the field. The second stage is when the frame is completely inside the field. And the third stage is when it's leaving the magnetic field. Let's start by analyzing it as 4 wire segments first before we analyze it as a coil. So, out of these 4 wire segments, only this one is cutting the magnetic flux. Do you agree? This segment is still outside the magnetic field, so it's not cutting any magnetic flux. These 2 wire segments are not cutting the magnetic field perpendicularly, as a wire segment is not even cutting out any area, right? So only this wire segment is cutting the magnetic flux. Using the Fleming's right-hand rule, you can figure out that this will be the positive terminal and this will be the negative terminal. So it's as if this wire segment behaves like a battery and it's going to push an anti-clockwise current through the circuit. As for the magnitude of this induced EMF, you can calculate using BLV. So B is the 0.8 Tesla, L is the length of this wire segment, and V is of course the speed at which the wire is moving. Okay, how about when the entire wire frame is inside the magnetic field? These 2 wire segments will still not be cutting any flux, but these 2 will both be cutting the flux. So same like last time, this wire will behave like a battery, like this, and this wire will also be behaving like a battery like this. Now notice that this segment is trying to push an anti-clockwise current, whereas this segment is trying to push a clockwise current. And since both of them is the same magnitude of EMF, we end up with no induced current. This is because the net EMF around the coil is actually 0. Okay, now the wire frame is leaving the magnetic field. So this time round, there's no induced EMF across this segment, but there's induced EMF across this segment. Do we have a net EMF around the coil this time? Yes, yeah? The net induced EMF is in fact 0.012 volt, and it's going to push a current this way, a clockwise current. Alright, now let's analyze it as a coil. So as a coil, we talk about the flux linkage of the coil. So at this point in time, there's this amount of magnetic flux, right? But as the coil enters the field, the flux linkage will become larger. Can you see? As the coil enters, the flux linkage will increase. Since this coil is experiencing an increasing flux into the screen, to oppose this change, it will produce a flux coming out of the screen. So using the right-hand grip rule, we can deduce that there's going to be a anti-clockwise induced current in this coil. Can we calculate the magnitude of this induced EMF? Of course we can. We use Faraday's law. So what is the rate of change of flux linkage? The flux is changing from 0 when the entire frame is outside to a maximum when the entire wire frame is inside. So when it's totally inside, the amount of flux linkage is the area of the coil times the magnetic flux density. But how long does it take for the flux to change from 0 to this maximum value? Well, the time taken will be the horizontal length of the wire frame divided by the horizontal speed that it's moving at. So 20 cm divided by 5 cm per second, that's where the 4 seconds come from. And we get the same number as before, 0.012 volts. Okay, now the entire frame is inside. Is there going to be any induced EMF in this coil? So notice, when it's totally inside, it's carrying the maximum flux already. So even though it's moving, the magnetic flux doesn't change. It's already carrying the maximum. So we can immediately conclude that the EMF around the coil is 0 and therefore no currents will be flowing. How about when the frame is leaving? So this is the amount of flux linkage As it moves rightward, the flux linkage decreases. So to oppose a decreasing flux linkage, the induced EMF will try to produce a flux that's in the same direction. So using your right hand grip rule to produce a flux going into the screen, we can predict that the induced EMF will try to push current in a clockwise manner. As for the magnitude of the induced EMF, well, the rate of decrease is the same as the rate of increase. So it's also going to be 0.012 volts. So whether we analyzed it as 4 wire segments cutting the flux or as a coil experiencing a changing flux linkage, our conclusions are exactly the same. An anti-clockwise induced EMF of 0.012 volts as it enters the field, no net induced EMF when it's totally inside, and a 0.012 volt clockwise EMF as it leaves the magnetic field. So it's up to you which approach you want to use. For me, I like to think of it as a coil when it's completely inside, but I prefer to think of them as a wire segment when it's entering or leaving the field. Alright, that's all. Ta-ta!